Back to calculus. We're going to go back over the problems I worked out last time, but this time with a clear audio. Just for reference, in case you ever do these videos yourself, I selected the wrong microphone probably, and that's why the sound didn't work out so well. Okay, so problem number 13, page 425. We want to integrate sine pi over 3 times t. So just use the formula I gave you in class. We know that the integral of the sine is negative cosine, but it's not that simple, of course, because of the pi over 3 there. That's what I call lambda. So it's 1 over lambda integral antiderivative of lambda x. So pi over 3 is lambda. Integrate the sine, that's negative cosine. Then you have to multiply by 1 over pi over 3, which is 3 over pi. That's where the reciprocal comes from. All right, or if you absolutely need to, just use the regular u substitution and you'll get the same answer. I just recommend use a shortcut. I think it'll be helpful. All right, number 15, basic u substitution. Let u equal 4x plus 7. And that'll work great because du is just 4 dx. And you could easily handle this extra 4. When you solve for dx, it's 1/4 du. And the 1/4 will just come right out to the front. So it almost instantly transforms from here to here. Once you have it du over u, integrate using the basic integral formula. It's just 1 over u. Antiderivative of 1 over u is natural log, absolute value, natural log of the absolute value. Then go back in and plug in what u is equal to, and you get that. All right, so that's old material, but hopefully it's just a little review from last time. All right, a more interesting u sub problem. So you look at this and you say, okay, looks complicated, but the derivative of this is basically 1 over that, right? So thinking ahead, the derivative of arctangent is 1 over x squared plus 1. So you could use that to your advantage, because if you let this equal u, du would exactly be this over this. So the integral transforms to u squared du. Easy integral, just a basic formula, u cubed over 3. Go back and plug in the value of u in terms of x, and you get the final answer. All right, average value, page 475, number 7. So it's just an integral, a definite integral, with a 1 over b minus a out in front. Finding the average value of a function is just doing an integral. That's it. There's really not much more there. But how do you do the integral? Well, u equals, this is cosine of x to the 4th power, right? There's really, don't forget, when you see something like cosine to the 4th x, that's the same thing as cosine of x quantity to the 4th. So if you make that equal to u, du will be negative sine of x dx, which is pretty much what you have except for the minus sign, which is easily, a minus sign is a negative 1. Constants and negative 1 are easily dealt with. They just come right out of the integral. Okay, so let's see what we're doing here. So u is cosine x, du is negative sine of x dx. We have a sine of x dx, so let's move the minus sign to the du, right? Multiply both sides by negative 1. Transform the limits. Let's get rid of the x's once and for all. When x is 0, u is cosine 0. When x is pi, u is cosine pi. Okay, so the integral transforms to this. Looks like I forgot to put the, oh, or maybe I didn't forget. I just wanted to show you the integral and how it's going to change the order. So, but I put it in there anyway. All right, so bottom line, you could switch the limits and get rid of a minus sign. That's allowed. That's one of the rules of integration. And then you're left with this. And once again, another shortcut. This is an even function, so you could simply double the integral from 0 to 1, since you get the same answer from -1 to 0 and 0 to 1. And you get 2 over 5 pi. All right, 2 over 5 pi. All right, that's page 1. Page 2. Another average value, but a little more interesting. We want the average value on page 475 from 0 to 12. So 1 over 12, the integral from 0 to 12 of that function. All right, so integrate the 50, that's 50t. The 14, just hold it to the side. And then this is lambda. Use the lambda equation from the last page. You just flip over the lambda and integrate the sign, and then keep the original lambda t. All right, so this is your basic antiderivative. This is not hard. So if you're finding this confusing, you have a lot of work to do, but it should not be hard. All right, then plug in 0, 12 and 0 and subtract, and you get 59.91. Okay, then the problem asks, is there a time when the temperature is exactly equal to the average temperature? And the answer is yes. As long as the function is continuous, there always is. So we simply set the value of the function equal to 59.91. So solve for t right here. Subtract, divide both sides by the 14, take the inverse sign, right? Take the inverse sign to get this, to get rid of the, to get the pi over t out of the, pi t over 12 out of the sign. And next, simply solve for t. I'm focusing, don't worry. Okay, solve for t, and t is equal to 3. So basically at 12 o'clock, so we start at 9 o'clock. 9 o'clock is 0. At 3 hours past 9 is 12. T equals 3. The temperature is the average temperature for the day. All right, number 7 on page 490. This is a basic integration by parts. It's not u sub. If this was an x squared, it would be u sub. But there's no way to get du to hold the x dx if it's just at 10x there. So u sub will not work. You need to use integration by parts. But why does it work so well? Because if you let u equal x and this equal to dv, v is easily calculated from dv. You just integrate. Du is dx. And using the integration by parts formula, u times v minus integral v du. Once again, you got to do the same kind of integral that you just did. Integral over cosine is sine 1 over 10. Another 1 over 10 comes out, so you got a 1 over 100. Right? All right, so basic integration by parts. Go through the steps one at a time if they're giving you trouble. But this is a pretty straightforward problem. All right, next page. Another integration by parts problem. This time it's a natural log version. So typically you let u equal the natural log of t. And dv would be t to the fourth dt. It'll be everything else that's left there. U is ln of t, dv is t to the fourth dt. V is the antiderivative of dv. Du is 1 over t dt. It's just a derivative of natural log with a dt thrown in. Go to the integration by parts formula. And notice here, you have to simplify. Don't just try to separate these out. That's not allowed. You have to simplify. T to the fifth over t is t to the fourth. Right? Do the integral properly. You get 1 over 25, t to the fifth. Final answer is right over here. It's just bringing down this to here, and that integral is worked out here. All right, here's another version of integration by parts. This one has a definite integral. So once again, u is the natural log. If there's a natural log, you always let that equal u. All right, dv is whatever's remaining, r to the minus 2 dr. V equals negative is the antiderivative of this, which is negative r to the minus 1. That's just the n plus 1 rule. Du is the derivative of the natural log. It's 1 over r dr, which is the same thing as r to the minus 1. All right, so going to the integration by parts formula. This is the definite integral version. Notice you just put the 1 and 5 here and the 1 and 5 there. This integral is r to the minus 2. Integrating that, once again using the n plus 1 rule, it's same thing we just did. Negative r to the minus 1 over minus 1, which is simplifies to that. Plugging in 1 and 5, we get this, and you get a nice final answer like that. Another example of integration by parts. If there's only one thing, one function in the integral, that pretty much has to be u. There's no other choice. U is inverse cosine, dv is dx, x is v. Du is the derivative of the inverse cosine, which is this. All right, so we go to the integration by parts formula. U times v is over here. And we get a complicated looking integral here, but it's really not so hard. It's just a simple u sub. You write it as u to the minus 1/2, and you let u equal 1 minus x squared. Du would be negative 2x dx. X dx, that's what we have. That's what we have to get rid of, right? That's simply du over negative 2. So integrating, negative 1/2 comes out to the front. U to the minus 1/2. It's u to the 1/2 over 1/2. Go back and plug in x cosine. Plug in the. Go back for this little integral, the subintegral, and plug in 1 minus x squared. And that will take care of this term here, which is that. So the integral of this is this. And the work for that is here. It's just a u sub. It's a u sub problem. All right. Some partial fraction problems. This is a case 2. Just make sure you do 1 or 2 problems from each case. Preferably do 2 problems from each case. All right. Case 2, because this is a repeated root. See the x plus 1 squared. It's repeated one. It's repeated twice. Here's the case 2 decomposition. Be careful here. Don't mess up in the first step. Clear the fractions. Multiply everything by this denominator, and you get this. FOIL out everything and distribute, group and factor, equate like coefficients. That's what we did here. And then go to the calculator. If you don't know how to use the calculator, go on YouTube and you could find a good video on it. But I've shown you guys many times, so you probably, by now, you should definitely know. All right, A, B, and C, solve for. Then you go back and plug them into the original functions with their proper A, B, and C. Easy integral, it's just a natural log. Easy integral, it's just a natural log. Why? Because it's a u sub. U equals x plus 1, u equals x plus 2. This one, on the other hand, is also u sub, but it's not a natural log. It's a u to the minus 2. And that's the correct answer for that one. All right, so to finish the problem, you would evaluate from 0 to 1 each term, and then add them all together. You could use your calculator to check your work and see if you simplified to the correct answer. All right, an improper integral too. Two x to the minus 3 from 1 to infinity. That's the limit as t goes to infinity from 1 to t of 2x to the minus 3 dx. This is a straightforward integral, n plus 1 rule, right? Negative 3 plus 1 over negative 3 plus 1. The 2's cancel, and plugging in t for x, you get this. Double negative is a plus. I just wrote it like this in a different way. Finally, let t go to infinity, and this term goes to 0, and you get 1. So the answer is converges. This converges to 1. All right, and last page. Why is this an improper integral? This is a type 2 improper integral. The previous one we did was type 1, by the way. It's not continuous at 0. Look at the graph. At 0, it has a infinite discontinuity. Looks like this. Right? Memorize your graphs. You must memorize your graphs. So what we're trying to integrate is from here, from negative 2 to 3. So what we start with is the right side, and if we get a divergence, we're done, and we say the whole thing diverges. So we split it up into two integrals, okay? And we integrate this one and we integrate this one. Well, I'm just going to work on this one, and because I know what the answer is already, but we'll see in a second why. So let's just work on this one. We take away the 0 because that's the problem, and use a limit to the right as t approaches 0 from the right. You're basically cutting off right here. There's your t. We're cutting off the integral from t to 3 instead of 0 to 3. Integrating, you get this. Simplifying a little bit and plugging in t, you get this. Now look at this term is fine. There's nothing wrong with this term here. Right? Nothing wrong with that term. However, this term over here is a 1 over t to the third power times 1/3. As t goes to 0 from the right, what does 1 over t cubed do? Well, if you don't instantly know the answer to this, here's the graph of 1 over x cubed. Right? You can see it's going up to infinity. Another way to think, the way I taught my students, is 1 over 0 plus cubed. Take a small number really close to 0, but just to the right, and cube it. It's still going to be a small number just to the right of 0, and that's a plus infinity. So it's a limit of type 1 over 0 plus. All right, so I hope that was this video came out better. Good luck, everybody, and I'll see you all on Monday. You should really study well. You should do a lot of problems. You should memorize those 4 pages of equations. It's mostly stuff you learned in Calculus 1, but you definitely may need to memorize some things again. You should be able to do the problems on the review problems easily. You know, if you can't do those easily, you're going to have trouble on the test. So if you only barely understand them, you're not going to do well. You need to know them really well, so this way you could figure out appropriate level problems on the test. All right, take care, everybody. Have a good weekend, and I'll see you Monday morning. Make sure you sit in alphabetical order. I'll be very strict with that, and use the restrooms before the test starts. Otherwise, if you have an emergency, you'll have to reschedule a makeup test.